In this lecture, we go over some practical applications of the methods of finding maxima and minima. We will maximize areas, volumes, and profits, and minimize distances, times, and costs. The term optimization means to select the best element with respect to some criteria. In the simplest case, an optimization problem consists of finding the best available value of some function on a given domain. Usually, the most challenging step is to translate the word problem into a mathematical formulation. Our strategy for solving optimization problems is the following. The first step is to choose variables. Determine which quantities are relevant by drawing a diagram and assign appropriate variables. The next step is to find the function and the interval. Restate the problem in terms of finding the maximum or the minimum of a function f on some interval. If f depends on more than one variable, use the given information to rewrite f as a function of just one variable. And the final step is to optimize the function. Use the derivative to find the absolute maximum or minimum of the function. If the interval is closed, use the closed interval method. The rest of our lecture is devoted to working through several examples. Here is example number 1. A piece of wire of length 8 inches is bent into the shape of a rectangle. Which dimensions produce the rectangle of maximum area? We draw a diagram of a wire being bent into a rectangle. We denote the length of the obtained rectangle by x, the width by y, and its area by a. The length of the wire, 8 inches, is the perimeter of the rectangle. Therefore, we are given that the perimeter of the rectangle, 2x plus 2y, equals 8. Our goal is to maximize the area. The area of a rectangle is length times width, so A equals x times y. Since A depends on two variables, x and y, we cannot find the maximum until we rewrite the area as a function of one variable. This can be done because x and y are related. 2x plus 2y equals 8, which gives y equals 4 minus x. Substituting the expression for y into the formula for the area, we obtain a equals x times 4 minus x equals 4x minus x squared. This is a function of x alone. On which interval does the optimization take place? Since a side of a rectangle cannot have negative length, we must require x to be positive. Also, the side of a rectangle cannot be larger than half of the perimeter. So x has to be less than 4. Therefore, the problem reduces to finding the maximal value of function a of x equals 4x minus x squared for x between 0 and 4. Since we are looking for a maximum of a continuous function on a closed and bounded interval 0, 4, we use the closed interval method. The derivative of a of x is 4 minus 2x. Setting it equal to 0 and solving for x, we find that x equals 2 is the critical point. It remains to calculate the values of a of x at the endpoints x equals 0, x equals 4, and the critical point x equals 2. A at 0 equals 4 times 0 minus 0 squared equals 0. A at 2 equals 4 times 2 minus 2 squared equals 4. A at 4 equals 4 times 4 minus 4 squared equals 0. The largest area is 4, and it occurs for x equals 2. The corresponding value of y is 4 minus 2, which is also 2. Therefore, the rectangle of maximal area is the square of sides x equals y equals 2. Let's move on to our second example. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $20 per square meter. Material for the sides costs $9 per square meter. Find the cost of materials for the cheapest such container. We draw a diagram of an open box, where L denotes the length, W denotes the width, and H the height, and V the volume. We are given that the volume of the box V must be 10 cubic meters, and the length L equals 2 times the width W. Also, the cost of the base is $20 per square meter, and the cost of the sides is $9 per square meter. Our goal is to minimize the cost. Cost equals 20 times the area of the base plus 9 times the area of 4 sides. The area of the base is length times width, so we get 20 times W times L. Now we need to add 9 multiplied by the area of 4 sides. 2 of the 4 sides have areas length times height, and the other 2 have areas width times height. Thus the area of 4 sides is 2 times L times H plus 2 times W times H. The cost function depends on three variables: L, H, and W. To find the minimum, we need to eliminate two of the three variables and rewrite the cost function as a function of one remaining variable. We are given that L equals 2W. When we substitute 2W for L in the cost function, we eliminate L. Now let's use the information about the volume to eliminate H. The volume V is length times width times height and must equal 10. Solving for H, we find that H equals 10 over L times W. We substitute 2W for L from the previous equation and obtain 10 divided by 2W squared, which is 5 divided by W squared. Now we can rewrite the cost function using the formula for L and H we just obtained. The expression for the cost that we derived is 20 times W times L plus 9 times 2LH plus 2WH. When we substitute 2W for L and 5 over W squared for H, we get 20 times W times 2W plus 9 times 2 times 2W times 5 over W squared plus 2W times 5 over W squared, which simplifies to 40W squared plus 270 divided by W. This is a function of W alone. We will denote it by C of W. Notice that the width W can take on any positive value. Therefore, the problem reduces to minimizing the function C of W for W greater than 0. We can restate our goal as finding the minimum of C of W equals 40W squared plus 270 over W for W greater than 0. In this case, the interval where we need to minimize the function is infinite. Therefore, we cannot use the closed interval method as before. Instead, we will examine intervals of increase-decrease of the cost function to deduce information about the absolute minimum of the function. The derivative C prime of W equals 80W minus 270 divided by W squared, which after getting a common denominator equals 80W cubed minus 270 divided by W squared. Since we are considering only positive values of w, the denominator here is never 0. Therefore, critical numbers are zeros of the numerator. 80w cubed minus 270 equals 0. We solve for w and get w cubed equals 270 over 80. After taking cubic root, w equals 3/2, which is the only critical number. We use the number line to find intervals of increase-decrease. We pick test points to be 1 and 10. We substitute the first test number 1 into the formula for the derivative and get c prime of 1 equals negative 190. We plug w equals 10 into c prime and get c prime of 10 equals 797.3. Since the value of the derivative at w equals 1 is negative, it is negative on the entire interval from 0 to 3/2. We indicate this by a minus above the interval. Similarly, c prime is positive at 10, so it is positive on the interval from 3/2 to infinity, and we write a plus above. We see that the cost function is decreasing to the left of 3/2 and increasing to the right. Therefore, the lowest point on the graph occurs when w equals 3/2, and the value c of 3/2 is the absolute minimum. The minimal cost is c of 3/2 equals 40 times 3/2 squared plus 270 divided by 3/2 equals $270. The next example is the last one of this lecture. A box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such box can have. We start with a square piece of cardboard 3 feet wide. Then we cut out 4 squares from the corners. We bend the sides up and construct a box. Our goal is to figure out the size of the squares we need to cut to obtain a box of the largest possible volume. Let's denote by x the length of the cut square and by y the length of the base. Since the length of the side of the cardboard is 3, 2x plus y must equal 3. Our goal is to maximize the volume of the box. The volume V is height multiplied by the area of the base. The height of the box is the length of the side we bent, which is x. The base of our box is a square of length y, which has area y squared. Therefore, V equals x times y squared. As before, we need to rewrite the volume as a function of one variable and then find its maximum. We use the given equation 2x plus y equals 3 to find y equals 3 minus 2x. Substituting into the expression for volume, we get V equals x times 3 minus 2x squared, which is a function of x alone. Let's see what restrictions we have on x. First of all, x must be non-negative, since it represents the length. Also, each cut-out square must have the length smaller than half of the side of the cardboard. So x has to be smaller than 3/2. We can restate our goal as to maximize function v of x equals x times 3 minus 2x squared for x between 0 and 3/2. Since x takes values on a closed and bounded interval, we use the closed interval method. We compute the derivative of v using the product and the chain rule. V prime of x equals 3 minus 2x squared plus 2 times x times 3 minus 2x times negative 2. Factoring out 3 minus 2x, we get 3 minus 2x times 3 minus 6x. Critical numbers are the values of x where the derivative equals 0. In this case, they are x equals 3/2 and x equals 1/2. To find the minimum of v, we compute the values of v at critical points and end points of the interval. There are 3 points to check: x equals 0, x equals 1/2, and x equals 3/2. We compute v of 0 to be 0. v of 1/2 equals 1/2 times 3 minus 2 times 1/2 squared equals 2. and V of 3/2 is again 0. We conclude that the maximal volume of the box is 2 cubic feet. This is the end of our lecture.